So anyway, so unit 4 here is on vectors. Vectors are just basically directed forces, directed values. They not only have a magnitude, but they have a direction. Like speed is what is referred to as a scalar. It is just a value. You might be doing 55 miles per hour. That could be a speed. Velocity is a speed in a specified direction. So if you're going 55 miles per hour and then you turn and you can continue going 55 miles per hour, your speed has not changed. You're still going 55 miles per hour. Probably changed for a little while when you were turning, but overall it hasn't changed. Your velocity, however, has changed because even though your speed is the same, the direction is different. So that is considered to be a different velocity. So our analysis of vectors comes down to specifying that direction. And that direction comes back to that unit circle again in that grid, where 0 degrees, the initial side, of any angle, of course, is at 0 degrees. And we're looking at the vector being the terminal side of that angle. So that brown part there, the terminal side, is the vector. And let's say that is at 49 degrees. That would be the direction of that vector. So let's pull that vector out and look at it in more detail. So its direction is at 49 degrees because the 0 point is, if you want to think of it as being the east direction or the right-hand horizontal direction. That vector has an initial point. Just like an angle has an initial side, a vector has an initial point. Think of it as the starting point. It is the tail of the vector. It's the initial point. The head of the vector is what is referred to as the terminal point. So that's where the vector is. Now, there are a lot of things we can look at with these vectors. One of them is an inverse. To create an inverse of a vector, or to invert a vector, all it's asking us to do is to exchange the head and the tail. In other words, take the vector and point it in a different direction. A vector has two things. It has a line of action. The line of action is that line that it acts on. And then it has a direction. That head of the vector specifies the direction along that line of action. So an inverse or an inverted vector will have the same line of action, just the head is on the other end. When dealing with a vector, most often we deal with something called components. Components can be thought of in a couple of different ways. The official way, or the more technical way of thinking about it, are the horizontal and vertical pieces that are equivalent to the whole vector. Well, what does that mean? Well, what that basically means is you take from that terminal point, you create a triangle that contains our reference angle. So let's say this is still that 49-degree angle. So that reference angle is just 49 degrees. The components are the legs of that triangle. So the horizontal component is this length here. This leg of that triangle is the horizontal component. Now there has to be a direction on it. What direction is that going to point, left or right? To the right, exactly. Why is that? Well, because this end is at the tail of the vector, so that has to be a tail. This end projects up to the head of the vector, so that has to be a head. The vertical component is on this side. Is that vector pointing up or down? Up, right? The end that touches the vector has to match the end that it touches. So this touches the head of the vector, that has to be the head of that component as well. So that is the vertical component. And this down here is the horizontal component. So let's do some terminology here. That vector has two pieces. A vector has a magnitude, kind of like we saw with speed, 55 miles per hour with magnitude, and then it has a direction. The magnitude is going to be specified with the letter P. Why don't we use the letter M? Well, the letter capital M is used for a lot of other things, momentum and stuff like that. So the letter P is used for the magnitude of a vector. The direction, this one should be a shocker. Theta is our direction. So then the notation for the horizontal component. If this is theta here, here's our horizontal component, here's our vertical component. The magnitude of the horizontal component is P sub x. X means, horizontal, that's the horizontal variable on a graph. P sub x is the horizontal component. To find that, if we're using this here being P sub x, this here being P, the magnitude of the vector, is the length of that vector, using that angle, P sub x is which side of that triangle? It's one of the legs, right? Is it opposite or adjacent? It is the adjacent leg. P, of course, is the hypotenuse. What trig function uses adjacent and hypotenuse? Cosine. Our definition is cosine theta equals adjacent over hypotenuse. Well, if we fill in what we have here, cosine theta equals the adjacent P sub x over the hypotenuse of P. If I just multiply both sides of that by P, I get P sub x is equal to P times the cosine of theta. That is the horizontal component. Vertical component. Anybody want to guess what the notation is for the vertical component? Well, if we use P sub x for the horizontal, it's going to be P sub y for vertical. So yes, we call that piece of y, and you're right, which that is the opposite side. So what trig function is that going to relate to? We want to relate it back to p. Opposite hypotenuse would be sine. So sine theta is going to be opposite over hypotenuse. We put in the information we have. The opposite side is p sub y, and our hypotenuse is p. Multiplying both sides of that by p, we get that p sub y is equal to p times the sine of theta. So let's look at some vectors. Have you seen a second to get that down yet? You ready, Jordan? Okay, let me know when you're ready. You're good? Okay, so let's look at some examples. Let's have a vector. Most of the time, our vectors are going to be forces if we're doing vector analysis. It can be speeds and other things, but the most common is a force. So 250 pounds at 72 degrees. Find px and py. Well, px, what's p in this? 250 is p. What's theta? 72. So px is going to be 250 times cosine, remember, is always horizontal, 72 degrees. Make sure your calculator is back in degree mode, by the way. So 77.25. That was in pounds, so this is going to be in pounds as well. So px is 77.25 pounds. Py is 250 times sine of 72. Give us 237.76 pounds. So we have our horizontal and vertical components. If I were to try to draw out this triangle, this would be 77.25 pounds. This would be 237.76 pounds. And of course, this would be 250 pounds. Can anybody look at this and think of a way to double check these numbers? Exactly. 250 squared better be equal to 77.25 squared plus 237.76 squared. Now, before you punch that in, can anybody think of a reason why those might not come out to be exactly the same? Rounding. Yeah, these are rounded numbers. Yeah, well, that might be a problem too. 250 squared is 62,500. On the other side there, let's do 77.25 squared plus 237.76 squared. And we get 62,497.38. That is close enough. So that works. So those are the horizontal and vertical components of that. Get all that? I want you guys to do, still gonna use 250 pounds, but at 108 degrees. Find px and py for me in your notes. So for px, what'd you get? Negative 77.25. For just a second, let's look at what does that mean to be negative? That just means that from our starting point, it goes to the left. PY? 237.76. Right there. Now this makes sense because 108 degrees, if we think of this as being 0, that definitely does have to go past 90 degrees. So that's your 250 pounds there. Anybody, by the way, notice anything strange or similar about those numbers? If you look at the last example, they're the same numbers, aren't they? They're supplementary. The reference angle here would be 72 degrees. So there are actually two other vectors that would have those same components, just maybe different by positive or negative. If it was 250 pounds at 252 degrees, without doing any calculation, px we know is going to be 77.25. Positive or negative? Negative. Because that's still on, if we're looking at that circle, that's still over here. The y is negative. Py is going to be negative 237.76 pounds. What if we use 250 pounds at, what is it, 282 degrees, I believe? 288 degrees. Px is going to be positive, because over here, the x direction is positive. So that's going to be just 77.25 pounds. And Py will be the negative 237.76. And again, those work that way because 288, 252, 108, and 72 all have that same reference angle of 72 degrees. So that reference angle is important. Reference angle is even more so important if we're trying to go the other direction. If I give you Px is 80 pounds and Py is 150 pounds, I want to find the magnitude and direction, P and theta here. Well, we have to resort back to that unit circle. Px of 80 pounds is 80 pounds going this direction, right? Py of 150, that's 150 pounds going that direction. How would we find P? Hypotenuse. 80 squared plus 150 squared, right? Square rooted. What do you come up with? Double check me just in case. 170 is good. Okay, perfect. Now our angle, our direction, theta, is just this angle right here, isn't it? So we have the 150 is which side of that triangle? Is it the hypotenuse? No. Is it opposite or adjacent? Opposite. The 80 is then the adjacent. So we are dealing with a tangent here. Tangent theta equals opposite over adjacent. Well, we put in what we know. Tangent to theta, the opposite side is 150. The adjacent side is 80. So how do we find the tangent from that? Inverse tangent, right? Inverse tangent cancels out the tangent. Inverse tangent of 150 over 80 61.93 degrees. So that is 170 pounds at 61.93 degrees. What do you think? It doesn't always stay quite that easy. Let's say we have px of, let's go negative 80 pounds and py of 60 pounds. So again, we're going to draw this out. From our starting point, what direction do we go with px? We go left because it is negative. For y, py, up, and that's 60, positive 60 pounds. So then, of course, our p is right there. Theta is actually that angle. How are we going to find p? Pythagorean theorem. Square root of 60 squared plus, now notice I just put in 80 squared, not negative 80. These are links, right? So links are always really positive. The negative specify the direction, but we're really only concerned about the magnitude. Get 100 pounds. Theta is going to require a bit more work. If we come down here, we can find this angle right here. I'm going to call that angle A. How would I find angle A? Well, we have the opposite and the adjacent, right? Tangent. Tangent of A is equal to the opposite of 60 over, now again, I'm going to put in just the 80, not negative 80. I'm using the absolute value or the magnitude. So A is the inverse tangent of 60 over 80. Which is 36.87 degrees. So this angle here is 36.87 degrees. How do we find theta from that? Yeah, those are supplements. So 180 minus that is 143.13 degrees. So that vector is 100 pounds at 143.13 degrees. What you think? Not horrible? I want you guys to try one. If I give you that px is 240 pounds and py is negative 100 pounds, find for me for that vector magnitude and direction. Give you a couple. That reference angle is going to be the inverse tangent of 100 over 240. Notice we don't use the negatives, which is going to give us what, like 26.56 or 26.57? 22.62, okay. 22.62 degrees. So that's 22.62 degrees here. To get the actual angle theta, we subtract that from 360. So 337.38 degrees. So our vector there is 260 pounds at 337.38 degrees. What do you think? Good stuff? Why would you ever need to know this? Well, it all depends on what stage of the industry, what part of the industry you get into. Let's say you have a pole. You have wire going off in this direction, another wire going off in that direction. That pole, because of the tension in those wires, has to be supported. If you have a pole where the forces look like this, where the wires go off pretty much opposite directions, the forces on those wires balance each other out. There's zero, they call it zero torque on that pole. Well, if there's forces going in those directions, that pole is being pulled in that direction. Over time, it'll start to sag in, and it releases tension on the wires, and the wires start to sag. So you want to be able to put a support wire, a guide wire, in this direction to keep that pole from sagging. The amount of tension on that guide wire has to be such that it balances out the forces on those other two wires. So you end up with zero net force, called equilibrium. Equilibrium is something we will discuss more in future classes, but for right now, just know that that's found by breaking down those horizontal and vertical components and balancing them out. For example, this one here would be all horizontal. There'd be no vertical components of that, the way it's drawn. These two then would have horizontal and vertical components. These vertical components have to be equal because those are the only two vertical components. Equal but in opposite directions. So it balance out to zero vertical force. These two horizontal components have to add up to this one so that we have zero horizontal force. Again, we'll look at that more in future classes. For right now, you're going to get a worksheet on vertical and horizontal components.